chapter 430. There's a few things I would like you guys to highlight if you have not done that. So please go with your friend Chad to chapter 4, article 430, and let's have a quick tour before, so we can highlight the most important articles that you need to know. Okay, so again, everything that you guys need to know is going to be about motor is going to be in article 430. This is what the one line diagram that we're going to be drawn over here. Long story short, guys, we're going to be talking about feeders, disconnect for the feeder, overcomputation wires for the feeder, feeder conductor, and then we go down to the branch circuits, disconnect for the branch circuits, overcomputation device for the branch circuits, conductors for the branch circuits, and overload protection for the branch circuits. That's what we're going to be sizing for these babies. So a few things. So this table, if you guys have not highlighted this table comes very handy. Let me see if I get my highlighter. So please highlight this table. It gets you the layout of how this article is made. I'll make it. Motors, guys, are very complicated, so we're going to make it easier as we go through the whole year. So highlight this one, the most important thing. So what we're going to be talking about, guys, today, I'm going to talk about the feeders. I'm going to talk about the feeder overcomputation device. We're going to talk about the motor branch circuit and ground fault protection, motor conductors, controller, and we're going to talk about the controller circuit, no overload protection device. So these are the stuff that we're going to be talking about in this article. Could you please highlight these, guys, as we go through? So this is the single most important thing in this. This is, yeah. Okay, so we got that one. Am I going too fast? Should move slightly. Okay, so the second, everybody got that one? Everybody can see the correspondence of the feeder, for example, guys, the overcomputation device, the overcomputation device for the branch circuits, the controller, as well as the overload for these motors. These are the things that we're going to highlight and we're going to go over. So please highlight these. So let's keep going into a few things. So this is my motor definitions, all this stuff. The few things I want you guys to highlight and never forget, probably marking this table. If you have not highlighted this table, please do so right in here. This is table 430.7b, locked rotor indicating code letters. Locked rotor current, guys, give you the starting current of a motor. Who cares? The question is, who cares if I know the starting current? When you say based on the starting current, guys, your system can malfunction or not work properly. Example, every time you turn the air handling unit, the light will dim. Would that make the customers happy? Or every time you turn the air handling unit, the circuit breaker or the fuse will blow or the circuit breaker will trip. Would that make the customers happy? No. This is how you use this one, code letters. Every motor that we make in the US, guys, has a code letter right into it. The code letter indicates how high the starting current of the motor. From A being the lowest starting current into V being the highest starting current. Which do you guys think the best motor that you can have? The one that has the lowest starting current. Why the lowest starting current? Because the lowest starting current corresponds to no nuisance tripping, smaller equipment. So I want just you to highlight, guys. Here's A is the least. You always go with the multiplier, the worst scenario. And then you go V. Can you guys see V? And the worst scenario for V is 22.4, the multiplier. I'll show you how to use it.
What's the meaning of locked rotor?
Locked rotor current, if you grab the rotor and you lock it and you turn the switch on.
So when it's off, it's more considered locked?
It's really not off, it's on, but the challenge with motors, guys, is in order for motors to work, you have to have some type of rotation so you can balance you can suck current and convert it into mechanical energy. If you grab that conversion mechanism, which is the rotor, grab it, I hope not with your hand, grab it with some means and lock it and turn the switch on. So all this energy coming to the motor, trying to be converted to mechanical energy, fan, compressor, whatever, but it can't do it. So what happened is it starts heating up and heating up and heating up, and at one time it's gonna burn your motor. So the locked rotor current will give you an indication of a starting current. When you flip the switch, it's like the rotor is not running in. Exactly the same. The rotor is not running. So you're getting a very high inrush, they call it. Inrush, locked rotor current, starting current, inrush current. Bad news for the electrical system, we need to minimize it. Any question, guys, about this? So when I told you guys the locked rotor current is J for the equipment, then you're gonna go grab J here and always go to the upper always go to the upper limit. Why the upper limit? The upper limit gives you the worst scenario. Come on, buddy. The upper limit will always give you the worst scenario. Okay, so here is the upper limit. The upper limit will give you the worst scenario. Any question about this table, guys? I'll show you an example how to use this table. I want to bring to your attention that this table, if you guys highlight here, this table is actually amps per horsepower, kilovolt ampere horsepower. So when you use it, the formula that goes with it, if I have to get rid of my indication here. If you, okay, let's say hit escape. See if we can get that one back. No, can't get it back. Okay, I'll put the formulas in a few here. Okay. Comments, edit, undo. Okay, so any question, guys, about this other than the formulas that we're going to be using later on? I'll show you. But when I say go refer to this table, go always to the upper limit. Go always to the upper limit. Okay, the second table that you need to know, minimum wire bands. There's a few things, but from a design point of view, the few things that you need to know: location of motors. We need to go to conductors, multifunction conductor 21, motor conductor circuits, motor conductor circuits. And we need 52 overcome detection device circuit. Okay, 430.22. So 430.22 right here. Please highlight this one. 430.22 tool highlighter. Mark. If you have not highlighted this one, please do so. This is how we size the conductor for a motor, a continuous duty motor. And I want you guys to highlight in particular this number. It says 125. So you take the full load current from the NEC Codebook and you multiply it by 125. Okay, here's the article that I want you to highlight right now. 430.22. 430.22. Any question, guys, about 430.22? You take the full load current from the NEC Codebook, multiply by 1.25. Why do we do it this way? Because the code says so. Any question about that? Any question about this, finding this one? The second thing I want you guys to go is overcurrent protection devices. Overcurrent protection devices. Overload. Let's talk about overload is 430.20. 32. 430.32. Let's go to the overload a little bit. 31, 32. 32. Okay. The other one, guys, is I want you to highlight is 430.32 continuous duty overload. 430.32, and in particular A. And in particular to these ones right in A. Please highlight this if you have not done so. So this is 430.32A. Highlight where it says motors with a marked service factor 115, 125, service marked temperature rise 40, 125, all other motors 115. Please highlight these if you have not done so. Cool, everybody's there? Did you guys highlight these before? Did I walk you through highlighting them? No, I did another group, but not you. These are very important, guys, as you move forward. And I know my friend Chris is going to take all these tables down and automate them for us, so you don't have to go there. Okay, so this is for the overload. The second one I want you guys to highlight is an overcome protection device table. Overload overcome protection device table. This table, if you have not used this table, please highlight it. Very, very important table. Extremely important table. Which page would that be? This would be page 323. Thank you. 323. Please highlight this table. Edit, undo, dual. Okay. All right. Here's what this table is. If I ask you guys, there are 4 types of overcome protection device: non-time delay fuse, dual element time delay fuse, instantaneous strip, and inverse. So when I ask you, you're looking at inverse type circuit breaker right in this panel. So for example, let's take a single phase. Here's my single phase motor. Everybody's okay with this? Single phase motor. Pick one. What type of fuse do you want to use? You can use any of these 4. Pick one. What type do you want to use? Pick any one of these. Non-time delay fuse. Shall we do a non-time delay fuse? Your multiplier will be 30. So Chris does not like non-time delay fuse. He wants dual element. Gives a better protection. So multiplier 175. My friend Tao over there, he said he loves the instantaneous strip circuit breakers, a special type of circuit breakers. Your multiplier is going to be 800. And Phil, my friend, he loves these circuit breakers that's sitting right here. These are called molded scale circuit breaker, the last one, right? And he wants to use them with a motor. In a case like this, my multiplier for this one would be what? Inverse type circuit breaker, 250. What do? You take the full load current, guys, multiply it by these multipliers. Any question? So as I start going through the example right now, and I say you're going to go to 250, 430.52, inverse type circuit breaker, you know what I'm talking about, right? Everybody knows what we're talking about. Let's go 3-phase. Here's 3-phase. All the 3 phases are the same. Squirrel cage with energy efficient is a special. Design B, energy efficient is special here. AC polyphase motors other than wound rotor, squirrel cage other than design B. Most of the time you're going to be in squirrel cage. Synchronous motor, God forbid you do one of these. Wound rotor motor and DC motor. These are the major types of the motor you're going to be using. For this time, at this time, I'm going to be using single phase induction, squirrel cage, as well as single phase and 3-phase induction motors. Cool? Can I move on that away from that one? Make sure you highlight this one. You completely understand it. Multiplier for the overcome protection device. Okay, 53. You're going to highlight this one for the branch circuits. 430.60. 62. There is 6162 rating. Okay.
Are these devices installed in the panel, or are they usually in the...
You can install them in the panel. You can put them in a box like this. Most of the time they're in the panel. I want you to highlight this one, guys. Rating for or sitting for motors. For feeders. Now we're talking about feeders. I want you to highlight this, and I'll explain it as we go. The whole deal here. Right in here. All this. If you read this, rating or setting for motors 62, 430 to 62, it tells you to size the overcome protection device for a feeder. You take the largest, fattest, fluffiest overcome protection device in the system, and you add the full load current of all the other motors shared by the same feeder, and then you go down. If you read through all this junk, but please highlight it. Very important. That's how you size the feeder overcome protection device. Everybody knows what a feeder and branch circuit by now, right? Branch circuit overcome protection device, the one that protects the piece of equipment. Feeder protects multiple equipments, right? Could you please highlight this one? Very, very important. Okay, so we got that one. The last thing we're going to do is I want you to guys to go to 430.110. 430.110. All the way to 430.110 for disconnects. 11, 110. Okay, right here, please highlight this baby for me, and in particular highlight this. This will tell you disconnect. When you size the disconnect right here, when you guys size this disconnect, this is how to size in amps this disconnect. It will tell you have to take the full load current multiplied by 115. So please highlight 430.110A. Okay, any question guys about this? So these are the most important things that we need to go and size. One more I forgot. I'm going to make you guys go back. I'm sorry. Everybody highlight. I want you to go back to 430.24. I want to go to 430.24, please. 430.24. And let's highlight this one, and then we're done with highlights. 430.24. Where am I, Chad, here? 24, yep. You probably guys there before me. 430.20. 430.24. That we're talking about feeders. 24. Come on, Chad. Move it, move it. Okay, which page are we in? 430.22. We don't want 22. We're almost there. 430.23. 430.24. Right here. Please highlight this. All of this. This is how you size how we size the feeder. 430.24. You take the largest motor, multiply it by 1.25, and you add the full load current to that particular motor. In 2011, they changed a few things. They said, what if your panel that feeds motor also feeds light? Also, you take the light, multiply by 1.25 because it's continuous load. What if the same panel that feeds motor also feeds receptacle? You take the full load current of the receptacle because they're non-continuous. So long story short, that's how we size feeder that feeds motor. Cool? Everybody's okay with that? All right. So the last thing I want to do on this before we go directly to the example, since we highlight all these as you go through. Guys, by the way, when you finish as a designer, this book should be all highlighted. Hopefully by the time you finish with Chad. This is your reference. You know, you're the expert. You're going to be sitting on things. Okay, let's go back all the way. I'm going to go, guys, to table 430.250 way at the end. So if anybody way at the end, 430.250 all the way back. So if you are ahead of me, there you go. 430. Okay, let's start with this one. The NEC Codebook, guys, have the full load current of all the motors that are manufactured in the US. They give you a full load current. They start with this tiny little table. Which page is that one? Let me tell you the page here. The page is 336. I'm going to start at page 336. Okay, take this, my friend. Now here's where I want Chris to go automate this process for me. These are for DC motors. Unless you have a DC motor, don't even think about it. So I have a DC motor, 7.5 horsepower, and it's burning that baby at 240. What's the full load current for this baby? 29. Everybody knows how to use this table? Can you guys see that? I have a 7.5 horsepower motor. I am burning that boy at 240 DC. The full load current of that baby is 29. I have Oladipo said, I hate the guts of 240, Chad. I'm going to go all the way to 555. I'm going to go all the way to 555 volt DC. And I'm going to burn this baby at how much amps can get out of this if you go that high in the voltage. Look at the amps go down as the voltage goes up. Does that make sense? And that makes sense. Because the amps times the voltage equal the power. Horsepower is power. If you up the voltage, the amps guaranteed to go down. Any question how to use this table, guys? Okay, so this is the DC. Let's go back into 240. Let's go back to my favorite, which you probably will never see. This table, 430.248, full load current in amps, single phase. This is my single phase. Full load current in amps, single phase. This is what we're going to be using now. You can go up to 10 horsepower single phase. I decided, look how ugly that would be. My voltage is 115. The amp of a 10 horsepower at 115 is what? 100 amps. So Ashley, my friend, take this. The whole panel that you have in your house will be dedicated to feed just one 10 horsepower motor. That's why, guys, why we go three phase after that. The amps go so high on them. So 115 is high. So Chad, because it's 115, it's high, I'm going to burn it at 230. So go to 230. What's how much amps you can get at 230? Almost half. Double the voltage, you get half of the amps. Can you guys see that? The relationship? I want you guys to highlight this because it keeps confusing people all the time. I have Oladipo say, Chad, what the heck is 130? We don't have 230 in the US. Where the heck did you get 230? Can you guys see what I highlighted? From 110 to 120, you take 120. From 220 to 240, you go 230. Do you see the range that they give you right at the top? This here tells you from 110 to 120, you're going to be using 115. From 220 to 240, you're going to be using 230. 200 and 208, the motors have to be rated for 200 or 208. Does that make sense? Okay, so that's what we're going to be using. Full load current, two-phase, 4-wire. The one right next to it here, this is for two-phase system. God forbid that any one of you guys will work with these. So two-phase, everybody knows the difference between two-phase and three-phase and single-phase. Two-phase system coming from two hots with a 90-degree angle between, electrical angle between them. You rarely if ever, you will see this. Rarely if ever. So, but if you are to get into a two-phase system and motor two-phase, I heard that there's one building in downtown St. Paul that runs motors with two-phase. And don't confuse it with two-phase coming from a three-phase system, Ashley. This is not two-phase coming from a three-phase system. This is a two-phase standalone system. Okay, so we'll get that one here. It's supposed to 120 degree. Remember that three-phase system sits like this, the angle is 130 degree. The last and the most important one, guys, that I want you to highlight is three-phase. That's where being designers, where you guys are going to be all the time. Please highlight this. Please highlight also the bottom here so you know that the voltage range that you're dealing with. And I'm going to take all the way. So here's what you highlight. Chris, I have a 200 horsepower motor. Can you see that? I'm going to burn this baby at 200 volt. What's my full load current? 552. I'm going to burn it at 208. What's my full load current? 528. At 230 or 240, 480. I'm going to go all the way up to 260, 240. I'm going to go all the way to 576. That's 600 volt system. Can you guys see that? I'm going to go actually to medium voltage now. I'm going to go up to 2400, which is 2400 system or 2300 rating. Can you guys see that? Then there are two types of motors. The squirrel cage induction motor. That's where you're going to be 99% of the time. The second one is synchronous motors. And synchronous motors, very few of you guys will be dealing with synchronous motors. 90% of the time, Nick, you're going to be in induction motor. Any question? Anybody does not know how to find the full load current of the motor from these tables? Before we go directly to the example.
Use the nameplate as opposed to this?
There are two full load currents for every motor. One full load current, guys, is coming from the nameplate. That's used only for the overload. The other full load current coming from the NEC Codebook, and it's used for everything else. Remember this, you would never forget it. There are two full load currents. One on the nameplate, and it's only, the nameplate one is only used to size the overload. The table, the one from the tables, is used to size everything else. Now what the heck is everything else, Chad? Conductors, disconnects, overcaptation devices, magnetic starters, and all this stuff.
What's the difference between the overload and the overcurrent protection?
Good point. Overload protects you from overload. Here's what overload is. Suppose you have a pump that's supposed to pump water up to 2-story building, and you single-handedly, Chris, decided to install it into a 4-story building. You're overloading that baby. You're not short-circuiting it, but it's working hard. Two things are going to happen. Either you protect it from overload, or you're going to see smoke after 2-3 hours of running. Another example is you have a saw, guys, that's supposed to cut through, say, wood, and you slam that baby right against the concrete, and you keep pushing on it. Of course, things are going to be flying all over. But suppose you got it to lock and keep pushing on it, you're overloading it. It's not supposed to. Conveyor that's supposed to carry, Chad carried 210 pounds, and you put, Zach, another 220 pounds on the same conveyor. Now you overloaded that baby. Granted that we're not going to be standing on conveyors, but any question, guys, about this? Okay, so this is, let's go directly to the example now, since you guys are cool. Close this window. Okay, let's go directly to my example. All right, we're cool. Move in, Chad. Get that baby here. Okay, so if you guys grab these motors, and let's go size for them. Take an example of sizing to make my system worthwhile. I want to go to 430. Okay, I'm going to use a single phase system. Here's the example. Example number one. Example number one. What I'm going to use, guys, is the following. I have a disconnect with a fuse, and I brought it right here into a gutter. Inside my gutter, and I went with my fuse, overcome protection device, conductor, controller, overload, and a motor. And the same thing for each one of these. And I want to use the circuit breaker for this boy, just because. And I'm going to use only 4, guys, and you can get the hang of it. Fuse, controller, overload, motor. Okay, here's the information here's the system that I have, and let's go pick a 3-phase motors, full load, single amp. Let's use how many motors do we have? 1, 2, 3, 4. I'm going to use 3, 5, 7.5, 10. This is 3 horsepower, 5 horsepower, 7.5 horsepower, and 10 horsepower. And the voltage system, I'm going to use single phase. So my voltage system here is 240 volt single phase. 240 volt single phase. Cool? Everybody's okay with that? Okay, so that's basically what we're having. Now, in reality, this is how this will look like. In reality, as an equipment, this will look like a box that contain all these. All this stuff will be in a box. All this stuff would be in a box, okay? Just to show you and this baby here will be in a different box. And the gutter, my gutter, will be in a third box. Okay? How many boxes do I have? 4, 5, 6 boxes. 6 different boxes. Everybody understand boxes like these? You have 1 box for the disconnect switch for the feeder, 1 for the gutter. Everybody knows what a gutter? Bring your cable and tie them together, splice them, and tab into all these 3 motors. This is one way of doing business. Instead, what's the alternative? Feed them from a panel directly. What's the advantage of this? Cheap. Okay, so we have this. Let's go size the following for this. Any question, guys, about this system? Any question about it? So what we're going to be doing for this, I'm going to size the following. Number one, let's use, what did I use? I'm going to use green for sizing. So I'm going to go and size the following. The first thing I'm going to size, let's use a system branch circuit. Let's do the branch circuit. So this conductor here, I'm going to call it number one. That's a branch circuit. The second thing I'm going to size is the overload coming from the bottom. This tiny little deal here is number two, my overload. My controller is right here, number three. Number four, let's make sure that we probably have enough time. So this one will be number one. This overload, number two. This will be controller number three. Overcome protection device number four. Number five is the disconnect. Okay? Number five is the disconnect. Number six is the conductor. Number seven is the overcome protection device for the system. The overcome protection device for the system.
What's the difference between 1 and 2? They appear pointing at the same thing.
1 and 2. 1 and 2. 1 is the conductor. I should probably stretch that baby here down a little bit. Let me stretch this one. Okay, here we go. What was that? 3 horsepower? 3 horsepower. And let's go. This one, use the same convention. The conductor right here is number one. Number two is the overcome protection, the overload. Well, we already have number two. Number two. And let's continue. First, does it make sense? The conductor versus the overload.
Okay. And number 3 is?
Number 3 is the contactor, the controller. Number 4 is the fuse, the disconnect. Number 5. Number 6 is the cable, the feeder. Number 7 is the overload. That fuse. That fuse here. Okay, can we go size this? We're gonna do it twice, 3 times. We are twice, and Chris is gonna do it 3rd time. We're gonna do it by calculator, and we're gonna do it, guys, by hand. Okay, any question about this? I will write the names as I go. To help us do this, I need to give you a couple of amps here. Nameplate. These called nameplate. Full load amps, nameplate. So we have the 3. We're gonna run them at, what did you say, 240? 240. So I have here, I have 45 amps, and right here I have 50. I have 45 amps here. I have 35 amps here. I have 23 amps here, and I have 15 amps for this baby. These are the full load amps, the nameplate. All these are nameplate full load amps. Full load amps. Everything that you see here in blue is nameplate full load amps. Nameplate full load amps for each one of these motors. We need them. I need to find the starting current of these motors. So the code letter, the second thing I'm going to give you guys, code letter, and let's go from say A, B, C, and D for each one of these motors. Okay, are you guys with me? The code letter for each of these motors, A, B, C, D. Just pick them up, A, B, C, D. Cool, everybody understand what the system is? What do we need to do? We need to size it twice, based on the calculator once, based on and calculation by the code 2nd time. I will write the name of the equipment as we go.
Chad, can we take a break? before we
Take a break?
start?
You guys want to take a break? Okay. All right.
This will take a little while.
Okay. Let's go ahead and continue here. Okay. Before I continue, guys, anybody has any question about the problem that we have? Everybody knows what these 7 items are, from a branch circuit to overload to disconnect. Everybody knows them. I will write the name as we go through. So let's go ahead and start with number 1. I want to start with number 1. Number 1 is branch circuit conductors. Branch circuit conductors, not even closer to conductors here. Branch circuit conductors. I'm gonna make them, guys. So here's what I'm gonna do for the, what is it, 15, it was 3 horsepower, 3, 5, 7.5, 10. I'm gonna do them all together. 3 horsepower, 5 horsepower, 7.5 horsepower, and 10 horsepower. If you guys took these to table 430 dot, what was it, the table that we look, 248. 248, this is Miss table. If you guys went there, here's what you're gonna find. The full load current for each one of these babies starting 17, 28, 40, 50. So this will be 17 amp, 28 amp, 40 amp, and 50 amp. Anybody has any question? 17, right? 17, 28, 40, 50. Directly from the NEC Codebook. The full load current. That's the first thing you need to do. Find the full load current for these 3 motors. The second thing, any question about how to find them? Remember, they're single phase and the voltage is 240. Don't forget that your voltage is, what was the voltage here? 240 volt. So you're going to go under 230 because it's closer to 240 and it's rated, that's where the range is. Okay, second thing you need to do is you take, so this one, you're going to take 1.25, multiply it by 17. And then you're going to take this one, 1.25 times 28. I'm doing all of them together at the same time. 1.25 times 40. And 1.25 times 50. Do I have a calculator handy? Or should I use my calculator today? Mental exercise. This will be 21 amps. 21 amps. This will be 35 amps. This will be 50 amps. This will be 63 amps. Okay, any question, guys? So that's why do you multiply it by this? Why did we do what we did? Let's take you to the article that says branch circuit, branch circuit, short circuit. Okay, branch circuit. You're gonna go to 430.22. All this info is from 430.22. Okay, everybody knows where I got the multiplier. 430.22. Cool. 430.22. Right? That's where you get the 1.25 because they're branch circuit. The last thing we're going to find, my friends, is the conductors. The conductors, I'm going to call, so conductors, let's do, let's take the 21 amps, take it to 310.15 B16 under 75-degree column, and I need a smart individual to tell me why there and why this amps. Why do we go there? And why 75? They're motors. They're motors. For the most part, they're 75. So if you guys go to 21 amps, I need number 12, right? Number 12 can give me number 12. So this will be 3 conductors, number 12 T H H N. Let's go the second one, 35 amps, the same way. This will get me 35. If you guys go to 35 directly, 35, that will be number 10. 3 conductors, number 10 T H H N. The second one is 50 and 63. 50 is number 8 and 63 is number 6. So 3 conductors number 8 T H H N and 3 conductors number, what did you say? 6 T H H N, and these are coming from the 50 amp and this is coming from the 63 amp. Any question, guys?
Yeah,
Yes.
what are we finding in number 2?
What are we finding from number 2?
Yeah,
We're finding the branch circuit size. All this stuff is to find the conductor size. Now, Ashley, you can go put them in a conduit and move on. Right? You can go put them in a conduit. If you decide to group them, we have to do the rating and size based on the rating. You might get up with a bigger conductor. So take this, Zach. You decided to, why 3 conductors, by the way? This is single phase system, right? This is single phase system. So single phase system, how many conductors for 240 single phase system? 2. So I need a 2, I'm used to 3 phase. So this will, each one of them will be a 2, a 2, and a 2, and a 2. If it was a 3 phase system, crest will be 3. Where's the equipment grounding conductor? It's the EMT conduit that's going with them. Done. So now you can go group them, put them in a conduit, make sure you do the rating, and see if these conductors are still valid. Maybe at one, not today, but one time we'll group a problem like this and size based on the rating. So that's it. That's, you guys are an engineer. All you have to do now, I can put all these, how many of them? 1, 2, 3, 4 times 2, 8 of them. Probably you can put them in an inch conduit, but then you do it for bundling. 6 carrying conductors, 8 carrying conductors, that will give you 70. What is it? 70, right? If I remember right. So 70, yep, up to 870. So for number 12, for 30 times 70. So if we'll do this problem another time, guys, you're gonna see, if you do the math, these will be okay if you group them all in an inch for the rating. I just don't want to complicate it and do the rating now. We're assuming we're putting in conduit per motor. Any question about this? Everybody knows what a branch circuit is? The one that's going directly to that particular motor. May I move into the next stuff? Branch circuits, right? Oladipo, my friend. Oladipo. Well, you guys, since you are the interesting group, we're gonna go do it with a calculator. And I haven't done that, so I don't know how it's gonna, the sizing the conductors. Okay, here's my conductor. Grab your calculator, put it handy. Cool. All right. Now, are we single phase or 3 phase? Are we single phase or 3 phase here? Single phase. So go set your calculator for single phase, will ya? Single phase, which is set number 1, single phase. Are we sizing based on 75 because they're motors? Yep, so set yourself at 75. So your calculator should look exactly like mine here. Single phase 75 copper. Copper because Chad loves the copper companies and I'm vested on them. Copper, default is copper, always. Cool, everybody's defaulted to single phase copper. All right, let's go with the voltage. What's the voltage of this system? The voltage is 240, right? So 240, and hit your volt, will ya? Get yourself the volt first. Get yourself the volt. Cool? The voltage. Second thing, we're gonna do them one motor at a time. The second motor that we're gonna have is 3 horsepower motor. Chris, hit 3 and go to HP motor, not the HPTH, the theoretical. HP motor. I have a 3 horsepower. Look at the default here. Can you guys see the IND induction? You can change this one to synchronous. We're not gonna mess with it right now, but we're gonna do an induction motor. Cool? Up to this point, we're cool? Okay, so let's go find the amps. What was the amps of this from the NEC Codebook? 17. Is that true or what? 17. Cool? Now, remember, this is a motor. So when you size the conductor, you're going to size it based on 125, right? So you're going to go set and wire size. Number 12. What did we come up with? Number 12. Are we okay? You can't find two gentlemen disagree on one thing. Or usually, or lie. One gentleman might lie, but two maybe. Chris, depends where you are. Which part of the country are you in? Any questions about this? So number 12. Okay, so we're done with this. Let's go to the next motor. What was the next motor? Now remember, the voltage all the depot stays the same, so don't mess with the voltage. We're gonna go with the 5 horsepower motor. Here's 5, put horsepower right here, and hit the amps. What was the amps for 5? 28. Surprise, surprise, 28, right? Exactly what that came from the code. Zach, this is the powerful of this one. You don't have to even go to the code later on. You don't have to go to the code book. It's already loaded, the full load current of it. Then, because it's continuous load, remember, you're going to go set, and you're going to size the wire. And my wire is number 10. What did we come up with? Number 10.
Didn't we, now I came up with 10 without repeating at 125%. So
Oh, okay. Well, maybe, yeah, but that's not always the case, probably. Well, let's try it. Maybe you're right. Okay, so let's do the last one, guys. Oh, 7.5. Here's 7.5. And I'm going to go put them as a motor. I'm going to hit my amps. Here's my amps, 40. Yeah, perfect, Chad. And let me hit the wire and see if I can get it. Number 8. I came up with number 8. So you might not even need to hit the 1.25. Number 8. Okay, so let's do the last thing. I like to hit the number 8. Let's do the last thing. The last thing is number 10. Oh, come on. Number 10. And the same thing, horsepower motor. And I'm going to hit wire amps. The amps for number 10 is 50 amps, exactly what the code said, right? And I'm going to hit wire. It's number 8. See, that's where it got you into issues, where we have to do set. Okay, so that's why. So always do set wire size. I'll get you number 6. Okay, that's where the 125. Any question, guys, about how to use it? Zach, is it handy or what? All what you have to do is just put the voltage and the horsepower. And then later on, you guys are going to size the overload and the disconnect directly from that calculator.
Did you press amps on here? I want to see what it is.
My amps, 50 amp.
Alright, so it doesn't do the math on
No, it doesn't multiply the 50. It doesn't do this step here. It does it with the set and wire size. Any question, guys? So now you know how to use a calculator to find the branch circuit for any motor. Now remember, always set the calculator if it's single phase or 3 phase. Always set it to the 75. The mistake number 1, Phil, is you go set your conductor to 60 here. Now remember, so it's not going to replace you guys, this calculator. It's going to make you smarter, faster. Because you still need to know that we size motor conductor, we size them based on 75. If you set your calculator based on 60 here, all your conductors will be oversized. Cool? Okay, so let's...
What if your conductor is in the 60s?
Thank you. Why do we give you the option? What if you're using TW conductor to feed motors? I could be using a TW. Then here's what you do. Then you go set 60 and you size everything. Same process, except you change yourself to set 60 degree and you size everything based on 60. Cool? Done. Okay, let's go minimize this baby here. I'm going to hide it right in here. And I'm going to go into my next step. Okay, what was the next one that we need to find? Number 1, number 2, overload, motor overload. Number 2. Number 2 is overload. Okay, so the overload, if you don't know, I need somebody to give me the amps because I gave you the amps for them. Can Chris Can you give it to me in order? So for the, what is it, the 3 horsepower, I have a 3 horsepower,
15.
and a 5 horsepower, and a 7.5, and a 10 horsepower.
Okay, Chad, do you want the 21 amps or the 17 amps?
No,
I want the nameplate, the one that you wrote.
The
15.
nameplate.
Yeah, the
Okay,
nameplate.
17.
Thank you. These are given. 17 amp.
It's
Is
15
it
amps.
no, the 15
Oh,
should be
sorry.
15 amps.
23 amps,
15 amps. What's the other one?
23,
23 amps.
35,
35 amps.
and 45.
45 amps. And all these are name plates. These are name plates. These are name plates. That's what you start when you do the overload. Start with the name plates. Okay, if you guys go to the, for motors, do I have a service factor? Do I give you any service factor? No. Do I give you a temperature rise? No. I didn't give you anything. So if you don't know anything about the motors, the overload will be sized based on 150. So where do you find this info? Motor overload is 430.32a. So if you guys go to, please go to 430.32a, this one, and that's why you come up with this multiplier, 1.15, 1.15, 1.15, 1 times 1.15, equal. Okay, who's my calculator here? 1.15, did you do them?
17.25,
1 second. 17
.25,
point, anything, 17 point, make it to the decimal, 1 decimal. 17.3,
17.3,
3 amp,
26,
26,
5, 40.3, and 52.
Okay. These are the overloads. What do you do with the overloads? What do you do with the overloads? Leave them alone. So you're going to come up to the overload. Can you guys see this overload here? Reset overload. I have my overload right here. I don't know if you see that little screw. You grab your screwdriver, they are closer to you. These little dial here are my overload. You can come here and adjust them as close. Of course, this have to match you're sitting there. You have to adjust them as close to 17.3 as possible. So if you can't get 17.3, you have to get lower than 17.3, like 17. So we don't go up or down. If we can't get an exact number, go down. There's no standard numbers, my point is. Okay?
And is there like a visual display of that? I mean, is it
Yeah, there's, if you look there, there's 1, 2, 3, yeah.
Are these also called the heaters?
Thank you. They're also called heaters. Now, if you have electronic overload like this, it's easy because you can adjust them. If you have a heater, then you have to go to the manufacturers and buy the closest heater that you can get. So if you can't get 17.3 amps, which I doubt that you will, you're going to get 17 amps heater. Go low. This will, yeah, go lower if it's not standard. If not standard, I want to say if not standard, go lower. Okay? Does that make sense, this message here? That's it. That's your overload. What does the overload do? A half banana engineer like Chad bought a pump that's supposed to pump for a 4-story building and install it on an 8-story building. I overloaded that pump. A conveyor that's supposed to move 50 pounds, you put 100 pounds in it. It will work over, and the overload trips over time, guys. It might sit for half an hour, and then trips. Any question, guys, about the overload? Do we buy the overload? Usually we buy the magnetic starter, comes with an overload. Okay, let's go to number 3, motor controller. Oh, let's do it on the calculator. Yeah, overload on the calculator. So let's go grab my calculator and grab the overload for that baby. Okay, I want to remind you guys, we're going to do overload on the calculator. So I want to remind you, if you have done anything with your calculator, let's go and check the voltage. What's the voltage? Hit the voltage. Make sure the voltage is still 240, right? Hit it. It's 240. Am I still defaulted to single phase 75 copper? Good. All right. So let's start with the first baby. 3 horsepower. 3 horsepower, right? And can you guys see the overload? Where is the overload, Chad? See default overload. Can you see that here? Overload. Hit the overload. 19 point, if you hit, it's based on 115. The pace is slightly different. They pace it 430.32. Can you guys see that? And 19.55. I came up 115. The challenge with the overload, guys, is they don't know the full load amps of the motor. So what they do is they default to the code full load amp. It defaults to the code full load amps. Okay, here's my overload. What was supposed to be 17? My overload ended up 19.55 because I defaulted. Here's my multiplier, 115, right? Here's where it came from, 430.32, exactly what we said. And it's 19.55. The other one is 32. So be careful with these because it defaults you. Let's look at the amps. Can you do that one? Can you do take 17 multiplied by 1.15 for me, will you? Would you get 19.55? Yeah. So be very careful. The calculator default, because I don't know what the amps for it is, so it defaults for the amps that you want. So let me try to cheat it though. Let's say we know the full load amp. So I'm going to go 5. Can you guys see 15 and force a 15 amp on it? Just put 15 amps, force it on it. I haven't tried that one. Let's see if we can get with 17. Yep. I can force it to take the amp, the full load amp. Or if I don't know, sometimes we have no idea what the nameplate yet. You can use the default from the code. Okay, one more time. So let's go to the 20. Since I know, here's my 23. Put the 23 amps here and go force an overload. Overload 26, right? 26.5. Let's take the 45 amps. 45 amps. Force the amps on it. And let's find an overload. 51, right? 52 almost. What else? Did we do, miss anyone? 35. Did we do 35? 35 amps and go force an overload. Okay. Now I want to remind you, Ashley, that the overload is defaulted to 115. If your circumstances are different than 115, you cannot use this overload. Overloads, guys, sometimes if the service factor is more than 1, like 1 and 1.15, you can go for 125%. So this is, it really defaults to 1.15. Your default is 1.15. For all practical reasons, that's get you there, but you gotta be very careful though. Okay, 2 things. Number 1, if you just put the horsepower, it will size it based on the code full load current, unless you force the amps on it. And we know how to force the amps. Just type the amps and hit overload. Cool? Any question, guys, about sizing the overload? Okay, with this, let's go lower my baby here and go back into number 3. Number 3. What is number 3 again? Number 3. Magnet controller. I need to size the controller. The controller, I don't know if we highlighted the controller for you guys. I don't think we highlighted the controller. To size the controller, go to 430.83. 430.83. Can you please, if you go to 430.83, it tells you you size the controller based on the voltage and the horsepower. And let's go ahead and do it. So the first one is a 3 horsepower at, what's the voltage? 240 volt. And the second one is 5 horsepower at 240 volt. The third one is 7.5 horsepower at 240 volt. And the third one is 10 horsepower at 240 volt. So you size based on the voltage and and the horsepower. the horsepower and the voltage for them. Okay, now then you have your DeWalt handy. Everybody has DeWalt handy. Let's go find the NEMA though. We need the NEMA contactor. NEMA. So then take all these babies, take them, all of them, one at a time to DeWalt page 6-4. And this is what you get. For the first one, they're 240. For the first one, guys, 3 horsepower. Everybody's there. Can you guys go to 6-4 DeWalt? 6-4 DeWalt. And the last 2 columns, it says single phase above them. Everybody can see the last 2 columns say single phase. My voltage is 240, so you go to 230, 240. The 3 horsepower give me NEMA 1. Everybody can see that? NEMA 1. So I have the first one, NEMA 1. The second one, 5 horsepower. 5 horsepower give me NEMA 2. NEMA 2. NEMA 2. The 7 horsepower, it's page 6-4. In the last 2 columns, on the right, on the right hand, or the first 2 columns from the right, or the last 2 columns from the left. Can you see them? Right here. Okay. Can you see on look at the last column, which is 240.
Okay.
And okay, now go to the first column. The last column can give you in the horsepower. So if you go, I need, for example, the 3. Go all the way up to 3 horsepower. So see where it says 3 here?
Okay.
And then
if you go
across will give you NEMA 1. Now I need a 5. I don't have a 5, but I have up to 7.5. Right? Can you guys see that? So that will give me 2, NEMA 2.
You mean
That's confusion.
And what does this have to do with
15?
the National Electrical Code?
Well, that's how we size the contactors, the NEMA starters for your motor.
but it should be a
Does the National Electrical Code reference DeWalt?
No, you're a designer. DeWalt is supplement for you.
Okay.
Okay? You could NEC, for the NEC, you stop right there. The blue. Done. But guys, we're more than that. You're gonna be sitting that NEMA size. You're gonna buy these. You're a designer. You're gonna put the NEMA size on them.
Why are we doing
Yeah.
this?
Because we're designers.
No, I mean, could we have a little more explanation? than-
Yeah.
because
Why are we?
That's like saying because I'm an engineer.
Yeah. Why are we doing what we're
The square root of-
Thank you. Magnetic starter, guys, what we're sizing right here, we're sizing this contactor. We're sizing this contactor. Everybody's there? We're sizing this contactor. So you can push a button and start and stop the motor. That's what a controller is. Chris, do you remember what you did with Gary with push buttons? When you guys did the magnetic starter on the wall, right? Push button station, you push the button, start and stop the motor. That's what we're sizing, right? This one. Good point. Okay, NEMA 2. What's the second one? Also NEMA 2. NEMA 2. The third one, NEMA. The third one, guys, is 10 horsepower. I have to go to NEMA 3. NEMA 3. Any question about this?
Yeah, why do you say NEMA 1, NEMA 2, NEMA 3?
Because if you look at the top here, where at the top it says NEMA ratings for AC starters in ampere, horsepower, phase, and voltage.
Where did you get NEMA 3 by?
NEMA 3 is up to, I need 10 horsepower, so what's my next standard? My next one that can go all the way up to 50. I'm sorry, all depot?
It is magic.
Yeah.
You know, it's confusing.
Is that? Okay.
But Jackson understand it better and he showed it to me. I believe other people are confused.
Okay.
You know, you got to let them know how to trace it to the NEMA.
Okay.
rating. So that's what they are asking.
Good point.
Yeah.
The way we size the NEMAs, guys, NEMA make magnetic starters like these on the wall. They go from NEMA 1 all the way to NEMA 9, single phase and 3 phase. Most of the 3 phase go to 9, right? So when you call the vendors, say I need NEMA 1, they will get you a NEMA that can handle up to, based on the voltage, the horsepower in this table, right? Cool. So now I'm giving you the voltage. I'm giving you the voltage, and I need you to find this, the NEMA. So which voltage? You're going to go to the last column that says 240. Everybody see 240, 230? Right underneath it is the voltages that can run, the horsepowers that can run at these voltages. So if I need, for example, if I need 10 horsepower, I can either go 7.5, that's too small because I need 10, or I have to go all the way up to what? 15. If you cross-referencing it all the way, it gives you a NEMA 3.
Okay, I see. The motor horsepower wasn't clear to me.
Oh, the table has horsepowers. Yep.
Yeah, I see that now.
Okay.
Okay.
7.5, you have it twice.
Yeah, because we don't have five.
Because
We don't have five.
NEMA 2, because there is no 5. If you don't have a 5, you have to go either to 3 or to 7.5. You can't go to 3, so you have to go to 7.5. Any question, very important guys, keep bringing it because I don't think you've ever seen this table before. Any question about this table? This is going to be second nature to you as we go through the design. Any question about that? Now we're going to go do in the calculator in a second. See if we can come up with the same answers. Cool? All right, let's go do in the calculator. What happened? They lost. Okay. Escape. There you go. Come on, too many things running. Close this. Okay. I don't want to sit into Explorer. Wow. Look at that calculator. How's that for you? Okay. All right. Give me my calculator, would you? So I'm there. I'm going to go get my calculator. Close this. All right. So come on. All right. Accept. Okay. Got my calculator up and running here. Anybody tried it? There you go. Okay, let's guys go do the calculator. Try to find the magnetic starter. It's single phase. Can you guys default your calculator to single phase? Set single phase. Everybody set single phase and set 75. I always like this because it's motor, so it's single phase set, right? Cool. Let's put the voltage. The voltage that I have. Go back. Overload contactor. The voltage that I have is 480, so 240. So 240, and put my voltage. The horsepower that I have, the first horsepower, 3 horsepower. 3 hit horsepower. Can you guys see, Nick, can you see the starter right above the horsepower? So you're going to go set and hit starter. NEMA what? NEMA 1. You got the NEMA 1 directly. Can you guys see that? You have to hit set horsepower again. Let's do it to the second one. The second one was 5 horsepower. Here's 5, hit horsepower, and then go set and hit horsepower again. That would be NEMA single phase. NEMA. Did I do it right? Did I 5? Okay, this is the 5 and horsepower. Okay, and set and horsepower. 1P. Still giving me NEMA 1. Even though that gave me NEMA 2 based on DeWalt. Okay. Let's.
What does the P stand for? The first time it didn't give us a P.
Yeah. Let me see if I can get that one again. Okay. 5 horsepower, single phase. Still says 5 horsepower, transfer. Let me try the 7.5, would you? 7.5 and horsepower. And I need to set and starter. Give me 2, so that's okay. Let me see the 10. The 10 horsepower and set and find the starter. None. So there is no based on this calculator. Okay. I've never used it for so 10. You highly unlikely you're gonna guys find 10 horsepower in single phase 240. It's not a common size. give you 250 amps, not a common size. That's probably why they don't carry it. The one I don't understand why the 5 horsepower did not give me 5 horsepower. Set and calculator, give me 1P, one single phase. So, okay, so for the test or anything else, guys, please give me use the DeWalt. DeWalt is standard. So up to 5, we were able to get number 2. All right. Okay, let's go to number 3. Number 4, quick here. We're getting in there. Number 4. What was number 4, quick? Number 4. What was number 4? Number 4 was overcurrent protection device. Branch circuit overcurrent protection device. Branch circuit overcurrent protection device. Branch circuit overcurrent protection device. Very cool. I want somebody to give you guys the 3 horsepower. 3 horsepower. You're gonna go to table directly. So let's do the math right on the spot. For the branch circuit, we're gonna go to 430.52. 430.52 table. And now we're gonna ask me what type of overcurrent protection device do you wanna use, Chad? I'm gonna use inverse type circuit breakers. I'm telling you, inverse type circuit breakers. So I'm using inverse type circuit breakers for all of them. And here's my 5 horsepower, 7.5 horsepower, and this is the 10 horsepower. Okay, so if you guys go to table 240, 430.250, 430.52, it will give you what's a multiplier? 2.5. Okay, so do me a favor here, Chris.
Oh, it's not 250?
250, which is 2.5. 250% is 2.5. It's percentage.
Oh,
Yeah.
okay.
Okay, times, what's the full load current? Can you give me the full load current now, not the nameplate that I gave you guys for these babies?
17.
Times 17. The second one is 2.5 times, what was it, 40?
28.
28, thank you. And 2.5 times,
40.
thank you, 40. And 2.5 times, 50. So these are not the nameplate, they're tables. Anybody has, Chris, did you get them? With your calculator? Or your,
Chad, can we just slow down just for a second?
Okay, go ahead.
And go to that code.
Yeah, let's go to that table.
2.5.
Yeah, go ahead. Can I run the calculation? I'll stop. Just
Yeah.
and I'm not gonna move anywhere. I just want to
Yeah.
put the calculation. Okay. This one is 43.
Yeah,
43 amps.
66.
66 amps. I will stop. I promise you, Nick. The second one,
101,
101 amp.
and I'm gonna outrun the next one up to 130.
130 amp. Okay. All right. Everybody went to table 430.52, guys. The last column is the inverse type circuit breaker. Did you guys see? And it's single phase motor. So the last column, first row, would that give you 250%, Nick? The last column, first row.
Inverse time circuit breaker.
Yep. Yep.
Okay, so it's percent.
Makes sense? Good point. So the first row, last column, right? Is that okay? Now I don't know about you guys, but I have no idea what these circuit breakers are. What size? Can I find a 101 circuit breaker? I can't find a 101 circuit breaker. So the next step that you need to do is to take the 43, take them to 240.6. Please go there, and your next standard here will be 35 amp. Go up. If it's not a standard, go up. So here's my first circuit breaker. The second one is 66. 66, that will get me 70. I think there's 70 amp, no? I want you to check that one. And 101, what's the next standard? I have 110. I believe there's 110 circuit breaker. And 130, will give me 150. I think it's 150. I'll check him in a second. 150 yeah. These are the standard circuit breakers that we use in the industry.
I think there is a problem in the calculation.
There's a problem in the calculation?
Yeah. 2.5 times 28 is 70.
2.5 times 28 equal 70.
Yeah.
Yeah.
Then
Chris,
the
what did
next
you
one is
multiply by?
100.
Sorry?
This should be 70.
Yeah.
Okay, thank you.
I carried the numbers from the previous calculation down.
The other one is 100.
This one just 100?
Yeah.
Oh, okay.
The next one 125.
100. What's the second one?
125.
125?
Yeah.
Even?
Yeah.
125. Chris, and the first one is true, 43? Everybody agrees? Okay. So, no?
Well, I copied the math from one, the results
Sale
from
to
one
another.
the other, so it's
Okay, not a
rounding-
big deal.
it's rounding issues, that's all.
240.
Or transportation issues.
So if you guys go to 240.6, we have to change these now, obviously. So this would be my 43 continues to be the same. 70 continues to be 70. 100. This actually becomes 100 now, right? Because we are at 100 amp. And 125 is the standard, right? So you continue doing 125. 125. If it wasn't the standard, where you go?
Go up.
Go up. Well, you came up with 125 even?
Yeah.
Okay. Where do you find these standard ones, guys? 125, 145, and 70. These are from Article 430.50. It's not really a table. It's an article.
When we're, taking the multiplier,
Give me 1 second here. 430. 4. Oh, 430.50.
are we taking the multiplier from the branch circuit conductors calculation?
No, we're taking it directly from the NEC code. That's probably why. See where we got them? Here's these are the amps that we multiply by 2.5.
Oh, okay, that's the deal.
Any question, guys, about number 4? Almost there, 3 to go. Number 4. Number 4. So these are the sizes of the. You know what? Since we already sized them, I think I might have lied to you a little bit. You guys remember we used some fuses? We use the fuses. We use the fuses on both of them. You know what? Since if it's a fuse, what do you use? What multiplier would you use? What type of fuse do you want, Chad? Since we're using the fuses, I forgot that we use the fuses.
Chad, what if we just run the fuse through the calculator? If we do it that way.
Do the fuses with the calculator? Okay, let me just change to be consistent here. Let me just change these into a circuit breaker. So all these are going to be circuit breakers. But I want to size the fuse. Okay. All right. We'll get. Let's assume, but we'll take him on the calculator. We'll do it on the calculator, like you said, just for the sake of the time here. Okay. If it was a fuse, you're going to ask me, Chad, is it non-time delay fuse? Then you're going to this one becomes 3. If it's dual element time delay fuse, this multiplier becomes 1.75. Can you guys see that from table 450.52, 430.52? So disclaimer, circuit breakers all. So we can size them by circuit. But do you guys know how to size them if they were not circuit breakers? If they are dual element time delay fuse, you multiply them by 1.75. Non-time delay fuse multiplied by 3 from the table. Okay, let's use the calculator on that baby. The calculator, okay, so here's my calculator. For the calculator, I'm gonna use first, all of them are circuit breakers, and we'll show you. Let's start with the 3, guys. Here's my, remember the voltage. Make sure your voltage is still 240. Hit your voltage, still says 240, okay? So let's go and put my 3 horsepower. Here's my 3 horsepower. And I need an inverse type circuit breaker. Can you guys see the inverse? Hit the inverse. What do you get? 43 amps. What did you get? What did we get here? 43 amps. The calculator actually does not find the 45 amp fuse for you, because the 45 amp fuse or circuit breaker is your choice. That's as high as you can get. So it does not size this for you. Are you guys with me? The calculator will not size the overcome protection device for you. It gives you the amps that you need to size it based. If you hit it again,
What horsepower are you on?
3. If you hit it again, it tells you, oh, by the way, here's your multiplier that I used for. If you hit it one more time, oh, by the way, here's the table that we came this information from. Isn't that cool? All right, so let's go calculate the 5. Let's do the 5. Here's my 5 horsepower. The same thing, I used inverse. Here's my 70, right? Came up with 70, hit again, 250, hit again, 430, 52, the table. Let's go to the 7.5, 7.5, right? And hit the horsepower, and I need inverse type circuit breaker, 100, even. Let's go to 10, last one, 10, and horsepower, and my inverse type circuit breaker is 125. If you hit this, 250, if you hit this, it gives you the table. Now, I'm gonna go size based on a fuse, dual element time delay fuse, the same calculation. I'm looking at 10 horsepower. So look how easy that. Do you see, Nick, do you see DE fuse? This is dual element time delay fuse. Yeah. So hit the dual element time delay fuse. Here's the fuse size that you need for dual element for number 10 horsepower. Now I changed my mind. I wanted a non-dual element time delay fuse. If you go set and hit it again, it will give you 150. Hit one more time, 300. Can you see that? It tells you what's the multiplier. Keep hitting it, give you the multiplier. Okay, let's do that for the 5 horsepower. One more time. Here's 5 horsepower. Hit the horsepower. I want to have a dual element time delay fuse. Hit this. Here's your dual element time delay fuse. 49. I need a circuit breaker. Hit the circuit breaker. 70. I changed my mind. I need non-time delay fuse. Can you guys see that right at the top? This is a non-time delay fuse, self-acting fuse set, and this one 84. I want instantaneous strip. Can you guys see that top instantaneous strip? Set this and find instantaneous strip. Look how the instantaneous strip, the size of the instantaneous strip, because the multiplier for the instantaneous strip is what? 800. 800. Cool. We will be using this calculator as we go, guys. I'm doing a residential what do you call them? A single phase. I will be doing 3 phase the same way as we go through. Any question? Everybody knows how. So now, Phil, I'm doing it in segments, but in reality, you put the horsepower and the voltage, and from that you can find the conductor size, you can find the overload, and you can find the overcome protection device directly from the same calculation, just by hitting a couple of buttons, and you can change your mind as you go. Okay, so we verified that. It doesn't give you the actual standard, so you have to go back and decide, are you going to go to the max or are you going to go lower? Which most of the time we go to the max because it's cover us. Any question, guys, about the overcome protection device? Yes, sir.
Excuse me, I want you to tell me why in the number 2 when we are calculating the overload, you said if it's not standard, we should go lower. But when we come to the branch circuit overcaptation devices, you said if it's not standard,
you go up. I told you to go up because if you go to table 430.52, if you read article 430.52, it tells you if you hit a non-standard, go up. So the short answer is because the code tells you to do so. I told you to go down in the overload because it doesn't tell you to go up. If you go read through the article, there's nothing that tells you to go up. So if you can't go up and you can't stay where you are, What are you going to do? It's only one street down. Now, if you ask me why do they do it this way, you go down in overload because overload is very important, guys. Your motors can burn a lot on overload. Short circuit is important, but not as sensitive as overload. Okay, so let's go to the number 5, guys, so we can move you to lunch. Disconnect. Number 5 is disconnect. Number 5. Number 5. Disconnect. Everybody knows what a disconnect is. We're sizing these bits. So disconnect the system to work on it. That's the reason for the disconnect. Okay, now, so I need the 3 horsepower, please. 3 horsepower. This is where you're going to go, guys. You're going to go to 430.110, and you have 1.15 times. Aladipo, what's the full load current of the? Give me the full load current for these babies. Was it 18? 17. And the 5 horsepower. 1.15 times 28. Thank you.
40.
And the and the 7.5 horsepower, 1.15 times 40, and the second one is 50, right?
Yeah.
Okay, 1.15, and this is for the 10 horsepower. And I'm typing it, I'm writing fast, guys, because we're repeating ourselves 4 times, doing the same thing. So I need somebody to give me the answers for these. Anybody?
Isn't it the same as? No, it's not.
1.15 times 17 equal 20 amp. 20 amp, right? 28 times 1.15 equal 32 amps. 32 amps. And 40 times 1.15 equal 46 amps. And 50 times 1.15 equal 58 amps. 58 amps. 58 amps. Up to this point you stop by the code, but because you guys are designers, we never stop there. You're going to go to the actual disconnect. So you're going to take 20 amp, take it to DeWalt, page 3-12. Nick, my friend, if you go to 3-12, right in the middle of a page, there is size of disconnects, standard disconnect, 3-12, right in the middle of a page. Very easy to read, it's just a bunch of standards. If you guys go there, there is no 20, the next standard is 30 amp. The second one is 32 amp, and from the same page, that will give me 60 amp. The third one is 46 amp, that will also give me a 60 amp. And the last one is 58 amps, that will give me also a 60 amp. Everybody can see these, where I came up with these numbers. The green thing is not code in this standards right here. Everybody can see where the disconnect, these you have to highlight, guys. Sizes of disconnect.
So in the code, it just has to be rated at or above the whatever.
Yeah. Yeah. Okay. Almost there. Almost there. Now, for the disconnect, you're on your own. This doesn't do a disconnect. You're on your own.
You have to use a range.
Yeah, you have to.
Or DeWalt.
Any question, guys, about this? Everybody got the disconnect sizes right in the middle of a page? Highlight them. All right, let's go directly to, can I move? Yes, no? All right, let's do 2 more and we're done. Number 6. Number 6 is feeder. Now we need to size. Number 6 is feeder conductors. The feeder conductors, guys, if you go to Article 430.2, go to Article 430.24, here's what it tells you. It tells you 1.25 times the largest, fattest motor. Oladipo, the largest amp motor was what? 50?
Yeah.
Right? It was 50. Plus 40. Plus 28. Plus 17 Oladipo.
Yeah.
Add them up. So you take the largest motor, multiply by 1.25, add the rest to it. 1.25 times 50 plus 40 plus 28 plus 17 equal.
The largest figure from where?
From the full load amp of a motor.
From full load amp.
Full load amp.
It's important to know what we're taking the largest of.
Yeah, 148 amps. Did you guys come up with something similar?
Yeah.
148 amps? Okay. Yeah.
I thought our full load amps was 45.
From the NEC Codebook.
Okay. That's a good question.
You take the largest horsepower motor, take the amps of that largest horsepower motor, multiply by 1.25, add the full load current from the NEC Codebook for all the other motors. Okay, so what do you get? Then
What table? The largest motor from the 430.32?
430 dot from no for the are you talking about the amps? Where you got the
Yeah.
amps?
Yeah.
You got the amps from table 430.248.
Okay.
248.
Good question.
Yeah. 148. Take it to table 310.15 B and 16 and 75-degree column, right? Every time you size a conductor, you always go to this table. So what's the conductor size, guys? That can get me that amps. 148, 150, 1 aught. So that will give me two conductors. Number 1. Did I look at the right one? Yeah, two conductors, 1 aught. 150. Two conductors, 1 aught. Done. How can I use this in the calculator? The best that you can do for the calculator, using the calculator, the best that you can do for this application is grab the amps, clear. What was the amps again? Amps, the total amps, 148, right? 148, and size, wire size, none. Why? Oh, because they didn't put amps, Chad. Take the 148, assign an amp to it, make sure it understands it's an amp, and go hit the wire size. Why not? Copper. It doesn't do the calculation for you. Gotta do something, as you said. So I wish you can put, it doesn't identify as a feeder. But the minute that you capture the amps, after you calculate the amps, then you just put the amps there and hit the calculator. So if you take the 148 one more time, hit amps, and remember you're not sizing base continuous, it's already taken there. Hit the wire. Don't hit set wire, that will multiply again by 1.25. So 1 aught. 1 aught. So Oladipo, my friend, you're not going to be able to size a feeder direct. You have to do some monkeying around. Okay, last thing, the overcurrent protection device for the feeder. That's the fuse or the circuit breaker. Any question, guys, about this? Okay, so grab this, lower it down so we can hide it. Go up, and I'm going to go to the last thing that I need, which is number 7, feeder overcurrent protection device. Feeder overcurrent protection device. The code for this one, you need to go to the code. The code says for this one, guys, 430.62. To understand it, 430.62. When I walked you guys at the beginning with these codes and said highlight it, the expectation is over the year that you're going to go read these articles, at least the ones that we highlighted. I'm going to tell you the summary. If you go there, it will tell you find the largest overcurrent protection device in the system. Overcurrent protection device. Add the full load current to it, and if it's not a standard, either you stay where you are and you custom design yourself a fuse, or the only way you can go is where? Down. Okay, so let's go. So what's my overcurrent protection device for the system? Remember the overcurrent protection device? We came up, here's, we're gonna go all the way to the overcurrent protection device, right here. So, Chris, what's the largest overcurrent protection device in the whole system here? 125. Okay? Take the largest.
And you're taking that from the inverse?
I made them all inverse here.
Okay.
Yeah. If it wasn't an inverse, if they were mixture, you take the largest regardless.
Okay.
So the largest overcurrent protection device. Do you guys agree with me? 125 is larger than all these circuit breakers? Okay, so take this 125 all the way. So 125 amp, I'm going to put it in brackets, plus. Aladipo, give me the full load current of all the others. Was it 40? Plus 28? Plus 17. Anybody can give me the answers for this? Everybody knows where the 125 came from? The largest overcurrent protection device. 125 plus 17 plus 40 plus 28 equal 210. I came up with 210 amps. You take the 210 to table 240.6. And if it's not a standard, you have a big fat arrow that looks like this. If it's not a standard,
Where did you get the string of 40, 28, 17?
That's
from
what I was
the,
Full load. Our full load.
the full load amps
full load amps.
from the NEC Codebook.
But I was thinking we're supposed to use the overcaptation values.
Oh.
You take the full load, the largest overcurrent protection device,
Okay.
and then you add to it the full load current for all the other motors from the code. Are these the code ones? These are the code ones, right?
Can you write the code number over the 40, 28, 17 that you're referring to?
These are coming here.
Yeah.
Okay, all these are coming from 430.248, right? 248.
All right.
Yep. Thank you. And this one, what was the code for that one here? That one was coming from 430.52. And next to it, what largest? Largest based on 430.52. Does that make sense? Okay, so what's the next standard down? I don't have 210. Do I have 210? Can you guys go there and see if we have a 210? Custom design yourself a 210. Chris, P and arm and leg for it.
I'm in the middle of writing something.
We should go to a 225.
You can't go to up. You can't go up.
Can't go up.
No. Because if you read through it, how would I know? If you go read through 460 dot,
Oh, that's right.
it's the feeders, the branch circuit we go up, the feeders we go down. Makes sense because we already went up. So what's the next standard down? 200? The next standard down is 200 amp. So my fuse and or in this case circuit breaker is going to be 200 amp.
That's from 246.
240.6, yep.
I think that count should be 240.6 or like that.
This one,
Yeah. The minus.
430.52, that's when we came up with the multiplier to came up with this one.
We went to 240.6.
This one is 240.6. NEC Codebook, Article 240.6.
Yeah, I understand what you're saying. But when you want to pick the largest from overcaptation devices,
Yeah, this one.
yeah, we go to Article 240.6.
Yes, yes. After you do the math,
Yeah, I was thinking you're
Yeah.
supposed to put the largest from the
you multiply it, and then you go to 240.6, find the actual standard. The actual standard from 240.6. What you're saying is here. Here, go back to the overcome protection device. Here's my overcome protection device, right? No conductor, branch circuit, overcome protection device. Number 4.
Yeah.
Okay, what you're saying, my friend, is not these numbers.
Yeah,
These numbers. See where we got them?
yeah. You see,
After you you went to 430.52, you
Yeah.
came up with 125. Then you checked under 240.6 if 125 is standard.
Yeah.
Happened to be a standard. If it wasn't a standard, we could have gone up here.
yeah. Now, what I'm saying is that since we got the values from 240.6,
Yep.
when we get to the feeders of our captation devices, we said we should take the largest. I thought you're supposed to refer to Article 240.6 since we are picking the value from there.
Yeah, I did for the feeder.
Now, you wrote a different thing. You said
240.
430.52. So that's what I'm trying to let you know that it's better we put it 240.6.
Okay. Here, this value here.
Yeah.
This value. Let me just use a green with it. This value is coming from 240.6 and from table 248 for largest motor. Did that help?
That's okay.
Okay. That value is coming from 240.6 and also from table 430.240 for the largest motor. Any question, guys? I gave you a single phase example. We will be doing the same example 3-phase as we go through the year. So by the time, guys, it's going to be a second nature for you to size all this good stuff. Now, Nick, my friend, you're on your own sizing this on the calculator. So, any question, my friends? That's probably cover 80% of what's in chapter 7, guys. I will refer to this next time. We'll do it for the review for the test or something. But then next quarter, guys, we will do 3-phase motors, do the same calculation. Hopefully it sticks in, and we'll do. Do me a favor, guys. Please review all the articles that are highlighted for you. Make sure you read them, study them, understand them. Yes, Chris? I'm done. So if you guys gonna go eat,